road in central Yakutia can look solid in spring and begin to betray itself by midsummer. The first signs may be subtle. A shallow dip where rainwater collects, a seam that no longer meets cleanly, or a ripple that forces drivers to slow down, and then the pavement opens. The shoulder slumps, and a route built across some of the coldest ground on Earth starts behaving as if the soil beneath it has been removed. That is exactly what thawing permafrost can do. It does not melt like a flat sheet of ice beneath an entire region. Instead, it weakens in patches where the ground contains buried wedges and lenses of ice. When that ice disappears, the space it occupied cannot support the same weight, so roads bend across new depressions, pipes lose alignment, and foundations settle at different speeds. In villages such as Chirupcha, the landscape around roads and homes has already developed the uneven pits and mounds of thermokarst terrain. In Yakutsk, satellite measurements have detected broad zones of surface subsidence, with the fastest measured areas sinking by more than 40 millimeters in a year during the study period. The frightening part is not that all of Siberia is dropping at once, it is that communities were designed around the assumption that frozen ground would remain a reliable foundation. That assumption is now being tested beneath streets, apartment blocks, airfields, pipelines, and the small roads that connect remote settlements to food, fuel, hospitals, and schools. And the latest Arctic climate record adds pressure to that story. The 2025 Arctic water year was the warmest measured since records began in 1900, and the last 10 years became the 10 warmest in that record. Across Yakutia, long-term observations show warmer air, a deeper seasonally thawed layer, and rising temperatures within the permafrost itself. A new monitoring system installed on a building in Yakutsk reflects the practical shift now underway. Engineers are no longer treating ground deformation as a distant possibility, and they are measuring it directly. Here's the central question: how can land that remains frozen hundreds of feet down still allow a city or village to sink at the surface? The answer begins with the active layer, the upper zone above permafrost that usually thaws each summer and refreezes in winter. And permafrost itself is ground that remains at or below freezing for at least 2 consecutive years. A road, house, forest, or field can sit above permafrost that is still technically frozen while the active layer grows deeper and begins reaching ice-rich material that had previously remained protected. Once the thaw touches that buried ice, the ground changes physically. Soil alone may compact, but ice-rich permafrost can lose a large fraction of its volume. In central Yakutia contains Yeroma, an ancient deposit of silt and organic material threaded with large ice wedges. Some wedges extend vertically for several stories, yet nothing at the surface reveals their exact shape, and a highway may cross one section with relatively little ground ice and another where ice makes up much of the subsurface. When warming reaches both places, they do not settle equally. That unevenness is what splits infrastructure. Picture a ruler resting across several blocks, and if every block lowers by exactly the same amount, the ruler stays straight. But if one block drops while the others remain high, it bends. A paved road responds in the same way, and its asphalt surface can stretch only so far before cracking. The gravel base shifts, drainage changes, and water begins collecting in the lowest points. That water can carry more heat into the ground, enlarge the depression, and accelerate the damage. And the same geometry affects buildings because many structures in Yakutsk stand on concrete piles driven into frozen ground, with open space beneath the floor so winter air can help preserve the cold foundation. That design works only while the ground around each pile keeps enough strength. If one cluster of piles loses support faster than another, walls crack, doors jam, pipes pull apart, and floors tilt. The building may still be standing, yet the process beneath it has already changed, and satellite radar has made that change easier to see. A study using 138 Sentinel-1 scenes from 2017 through 2021 mapped widespread deformation across Yakutsk, and the highest measured subsidence rates exceeded 40 millimeters per year, and the largest cumulative movement exceeded 1/4 of a meter. Those values did not mean every street sank by the same amount. They revealed a patchwork of moving zones, which is exactly the pattern most dangerous to rigid infrastructure. That distinction protects the title from exaggeration. Entire communities are not vanishing into one giant hole. They are beginning to sink unevenly, neighborhood by neighborhood and foundation by foundation by foundation, as ice-rich ground loses volume. Roads split because one segment remains supported while the next settles, while houses lean when one corner moves more than another. A settlement can continue functioning while spending more each year to keep the surface connected. The visible damage also hides a deeper contradiction. Siberian engineering has always expected extreme cold, but some systems built to survive winter can add heat during summer. Dark pavement absorbs sunlight, buildings leak warmth downward, and broken water or sewer lines wet the soil. And snow, piled beside a structure, insulates the ground from winter cold, and vegetation removed during construction no longer shades the surface. And each factor can deepen thaw locally, even as regional climate warming raises the background temperature. So the problem is not climate alone, and it is not construction alone. And the danger grows where long-term warming meets ice-rich ground, disturbed surfaces, trap water, and infrastructure that cannot tolerate differential movement. That is why one cracked road matters more than it appears to. It is not simply a maintenance failure on a remote route. It is a physical signal that the frozen foundation beneath a community is no longer behaving according to the old design assumptions. And stay with this story, because the next step is where the process becomes self-reinforcing. Once a road or building begins changing the flow of heat and water, the damage can help create the conditions for more thaw, and the most destructive permafrost failures often begin with a small imbalance. A ditch stops draining, water collects beside an embankment, and a culvert begins funneling heat or moving water toward ice-rich ground. And the ground settles by a few centimeters, which changes the slope, which traps more water, which transfers more heat downward. What started as a shallow depression becomes a maintenance problem that returns after every repair, and road crews can refill the dip and repave the surface, but asphalt does not restore the missing ground ice. If the thermal and drainage conditions remain unchanged, the new pavement may simply mark the beginning of another cycle, and that is why permafrost damage can look frustratingly repetitive. When the surface is repaired, winter freezes it hard, and then the following thaw season reveals that the foundation is still moving. To understand the movement, separate two processes that are often confused. Frost heave pushes ground upward when water freezes and forms ice lenses. And thaw settlement pulls the surface downward when ground ice melts and the wet soil compacts. A northern road can experience both movements within the same year. It rises and shifts in winter, then loses support in summer. Repeated cycles strain pavement, shoulders, bridge approaches, pipelines, and utility connections until cracks become permanent. In an ice-rich terrain, the settlement can be far larger than an ordinary freeze-thaw pothole. The former airfield at Churupsha offers a clear visual example. In terrain once leveled for a runway now contains swollen-looking mounds, depressions, wet patches, and standing water. A nearby section of the Kolome Federal Road crosses similarly deformed ground, and the road remains a transportation corridor, but the landscape beside and beneath it shows why keeping a straight, level surface is becoming harder. The village does not need to collapse for daily life to change, because a rough road alone increases travel time and vehicle damage. A broken pipe can leave homes without reliable water or heat. A tilted foundation can force residents to reinforce or abandon a building. A flooded depression can cut across a footpath or pasture. These disruptions accumulate, especially where there is only one road to a clinic, airport, fuel depot, or neighboring town. Yakutsk faces the urban version of the same problem. As the largest city built on continuous permafrost, much of its infrastructure depends on keeping the frozen foundation cold, and buildings are raised on piles, utility lines are often placed above ground for inspection and repair, and ventilated spaces beneath structures reduce heat transfer. These are standard design choices in the city. They are the engineering language of living on frozen soil, yet even a well-designed system has limits, and heat escaping from a building can create a thawed zone known as a talic, while leaking pipes can carry warm water into the ground. New pavement and denser development can alter snow cover, drainage, and surface temperature. When a foundation was designed using older climate conditions, a gradual rise in ground temperature reduces the safety margin before the soil loses bearing capacity. A 2020 Russian study described a deformation monitoring system installed on a Yakutsk building, not to announce an imminent collapse, but to detect small changes early. It was to measure tiny changes early enough that engineers could identify movement before it became a structural emergency. And that approach matters, because the most useful warning is rarely a dramatic crack. It is a trend in the elevation of a wall, pile, floor, or surrounding ground, and the same logic applies to roads. A driver sees one bump, while engineers can place temperature sensors through an embankment, survey the pavement repeatedly, use ground-penetrating radar to locate wet or weakened layers, and compare satellite images to map regional movement. Monitoring can reveal whether that bump is seasonal, whether it is accelerating, and whether nearby structures share the same deformation pattern. Research on road networks in Yakutsk and Norilsk shows why that distinction matters. Models that included existing pavement settlement produced much higher risk estimates than models that assumed an undamaged road. In other words, a road already beginning to deform is not merely a road with cosmetic flaws. It has less capacity to absorb additional thaw before its function deteriorates. Water is often the decisive amplifier because dry, frozen soil and saturated ice-rich soil respond differently to heat. When snowmelt or rain enters cracks, it can move along the road base and concentrate in low areas. Water carries heat more efficiently than air, and its movement can erode fine sediment. A depression, therefore, attracts the very material that can deepen it. And this is one reason a small drainage failure can matter more than a broad regional temperature average. Vegetation provides another protective layer as moss, organic soil, shrubs, and forest shade reduce summer heating. When construction strips that cover away, the darker mineral surface absorbs more energy. Wildfire can produce a similar change across a much larger area by removing the canopy and insulating organic layer. In central Yakutia, researchers have documented deeper active layers in thermokarst development where landscapes were disturbed. This does not mean every road crack in Siberia is caused by climate change. Poor construction, heavy vehicles, landslides, erosion, leaking utilities, and ordinary weather can damage pavement. A scientifically defensible story must connect thaw to evidence: warm ground, increasing active layer depth, ice-rich soils, measured subsidence, or deformation. And the title describes a regional pattern, not a diagnosis for every broken highway. The same caution applies to buildings. Reuters documented a damaged structure in Yakutsk where climate change and leaking pipes both contributed to thaw beneath the foundation, showing why the combination matters. Global warming sets a warmer baseline, while local heat and water determine where failure appears first. Blaming only one factor can hide the repair that is actually possible. This is the midpoint reframe. The sinking is not simply the ground responding to warmer air. It is an interaction between climate, buried ice, water, engineering, and maintenance. And the same temperature increase can produce little visible change on one block and severe settlement on the next, because the hidden ground is different. That hidden variability is what makes the problem expensive, because engineers cannot protect every kilometer of road in the same way. They must know where the ice is, where water flows, which structures are already moving, and which routes cannot be allowed to fail. The surface crack is only the final expression. The real hazard is the loss of a frozen load-bearing system that no one can see from the road. The scale of Siberia makes this hazard easy to misunderstand. Permafrost extends across immense areas, but its temperature, thickness, ground ice content, vegetation, and hydrology vary sharply. Some locations contain relatively dry frozen sediment, while others hold enough buried ice to reorganize the landscape when thaw begins. The future of a road or town depends less on the word permafrost than on the exact material beneath it. Yakutia is one of the clearest places to see that difference. Long-term analysis of climate and ground observations from 1965 through 2023 identified a strong modern warming period beginning in 2005. Compared with the earlier cold period beginning in 2005, mean annual air temperatures increased by roughly 2 to 2.5 degrees Celsius across Arctic and subarctic Yakutia. At the Tixi monitoring site, permafrost temperature rose by about 1.7 degrees at 10 meters depth and 1.1 degrees at 30 meters. Those numbers matter because deep ground changes slowly. A hot week can soften the surface, but it cannot instantly warm soil tens of meters below. When warming appears at those depths, it reflects energy accumulated over years. The system is no longer responding only to a single summer. It is carrying a long-term thermal signal downward. The 2025 Arctic record added another layer because surface air temperatures across the Arctic water year were the highest measured since at least 1900. Since 1980, annual Arctic air temperatures increased nearly 3 times faster than the global mean. That does not tell us exactly how many centimeters a Siberian road will settle next year, but it explains why design assumptions based on a colder 20th century climate are losing reliability. In central Yakutia, a scientific observatory at Serdok has tracked the connected behavior of soil temperature, water, river valleys, and ice-rich Yadoma. The research shows that thaw is not simply a vertical line moving downward. Watering, the worst in water, reorganizes the system as thermokarst depressions fill, drain, or expand. River valleys connect previously isolated wet areas, and ground stability changes while ice melts and sediment collapses. The famous Bataga kind look like when exposed. Ice-rich ground begins retreating back in years, but it is not the model for every settlement. Infrastructure more often fails quietly. A runway grade changes, a road shoulder lowers, a pipeline loses alignment, or a foundation requires another adjustment. None of those changes needs a dramatic crater to become operationally serious. A spectacular thaw feature attracts cameras, while a community pays for millimeters of deformation whenever a road, pipe, airfield, or building must remain level. Across the Arctic, models indicate that permafrost degradation could affect large shares of transportation and building infrastructure. One circumpolar assessment estimated that under a middle emission scenario, about 29% of roads, 23% of railways, and 11% of buildings could be affected, with total infrastructure damage costs reaching roughly $182 billion. A newer 2026 analysis, using improved maps of Arctic buildings, estimated median mid-century building losses of $76 billion under a middle scenario and $261 billion under a high scenario, though the uncertainty ranges were wide. And these are projections, not invoices that have already arrived. They combine climate models, infrastructure maps, engineering assumptions, and economic values. They cannot tell a family in Yakutsk which wall will crack or a road agency which culvert will fail first. Their value is different, and they show that localized damage repeated across thousands of structures and long networks can become a system-level cost. Russia holds the largest national area of permafrost, and many northern industries depend on roads, railways, pipelines, ports, power plants, and housing built on frozen ground. When support changes beneath one component, consequences can move through the network. A deformed road delays fuel, while a damaged pipe wets and warms nearby soil. A broken sewer creates a health problem and an additional thaw source. A shifting foundation can force a heating system offline during extreme cold, and that cascade is why communities can feel as if they are sinking even when the measured movement is only millimeters or centimeters per year. The experience is not one continuous descent. It is the growing number of places where the old level no longer holds. The doorstep below the walkway, a utility line no longer aligned, a road shoulder lower than the pavement, or a building that requires new supports. But radar has limits. It measures movement of the surface or structures that reflect the signal, but it does not automatically identify the cause. Seasonal frost, groundwater changes, construction activity, soil loading, or instrument geometry can influence the pattern. And scientists need temperature records, geology, engineering information, and field observations before attributing deformation to thawing ice-rich permafrost. This boundary matters because the phrase entire communities are sinking can sound like a prediction of abandonment. Any evidence supports a more precise and still serious conclusion. Whole settlements are exposed to uneven ground deformation that can damage many connected systems at once. Some neighborhoods may remain stable, while others may require constant repair. The hazard grows through accumulation rather than one dramatic moment. It also creates inequality because wealthier cities can install sensors, replace piles, redesign drainage, and rebuild roads. And small villages may have limited equipment, short construction seasons, and few alternate routes. A repair that is routine in a major city can become a regional emergency when the nearest replacement materials or engineering team are hundreds of kilometers away. And traditional land use is affected as well because thermal cars can change pasture, water access, and travel routes. In central Yakutia, degraded ice-rich land becomes uneven and waterlogged, reducing the area that can be used reliably. In the same process that deforms a road can reshape the fields and lakes around a settlement. For people living in Siberia, this is why the infrastructure story cannot be treated as a side effect of climate change. Permafrost is the foundation beneath the kitchen floor, the road to the airport, and the frozen ground holding a pipe in place. Once that load-bearing role becomes less reliable, the practical question is unavoidable. Can engineering keep the most important parts of a community stable while the regional climate continues to warm? There is no single technology that can refreeze Siberia, but local engineering can change how quickly heat reaches vulnerable ground. The first step is knowing where protection matters most. That means combining satellite deformation maps with borehole temperatures, ground ice surveys, drainage records, building inspections, and the lived observations of residents who know which road dips deepen each summer. The most familiar protection device is the thermosiphon, a sealed tube that uses cold winter air to remove heat from the ground without a conventional powered refrigerator. Fluid inside evaporates near the warmer base, rises, releases heat to the air, condenses, and returns downward. And thermosiphons stand beside buildings, pipelines, and embankments across coal regions like metal stems growing from the ground. They are useful, but not magic, because performance depends on sufficient winter cold, correct spacing, ground conditions, and maintenance. And as winters warm, the period when they can extract heat may shorten. Active cooling can provide more control, but it requires energy and costs more. Researchers are testing hybrid systems, insulation, reflective surfaces, and solar-powered cooling to extend protection where passive methods no longer provide enough margin. Roads require a broader toolkit. Engineers can raise the embankment, use coarse rock that promotes air circulation, install insulation, improve culverts, keep water from pooling, and build surfaces that absorb less solar energy. Some designs allow cold winter air to move through the road base, while others place thermosiphons along the shoulder, and the correct choice depends on whether the main problem is ground ice, water, heat from the surface, or all three. Drainage may be the least dramatic and most important intervention. A road that sheds water can remain stable longer than one that funnels meltwater into its own foundation, and ditches must stay open. Culverts must handle changing flows, and repairs must avoid creating dams that redirect water toward buildings. In a thawing landscape, water management is thermal engineering. Buildings also need ventilation beneath their floors and strict control of leaking utilities. The open space under a pile-supported apartment block is not wasted architecture. It prevents indoor heat from entering the ground, enclosing that space for storage. Allowing snow to pile deeply around it or running warm pipes without insulation can weaken the original design. New structures can be adapted to warmer conditions, but existing communities contain decades of construction built under different assumptions. Retrofitting every foundation is expensive, and some buildings are already too damaged for simple reinforcement. Planners therefore need a hierarchy, protect hospitals, heating plants, water systems, evacuation routes, airports, and the roads that connect isolated settlements before lower priority assets. Then there will also be places where holding the old line becomes unrealistic. Arctic risk studies describe decommissioning or relocation as possible responses when repeated damage exceeds the value or safety of continued repair, but that decision is not purely technical. A village is a community, not a collection of structures that can be moved like equipment. Cultural ties, indigenous land use, employment, schools, cemeteries, and access to traditional food all shape what adaptation means for Siberian settlements. The evidence does not justify declaring a mass relocation now. It does justify planning before the most important systems fail, and the dangerous pattern is waiting for a road to break, restoring the surface and ignoring why the same section keeps sinking. Climate action and local adaptation operate on different clocks in reducing greenhouse gas emissions limits, future warming, and the long-term depth of thaw. Drainage, cooling, monitoring, and better construction protect a specific road or building over years and decades. And one does not replace the other, and without global mitigation, the engineering challenge keeps growing. Without local adaptation, communities face damage from warming already in the system. The current observations from Yakutia make that timeline clear. Permafrost temperatures have risen at depth since the mid-2000s, and Yakutia shows thermokarst reshaping land around homes and transport routes. And the 2025 Arctic temperature record confirms that the regional warming background has not disappeared. And the 2026 monitoring work in Yakutsk shows that engineers are building systems to watch structures continuously. And what scientists cannot provide is a date when a particular neighborhood will fail, because permafrost does not behave like a countdown. Ground ice is hidden, local heat sources differ, drainage changes, and weather varies from year to year. A cooler summer may slow movement, while a wet or unusually warm season can expose a weak section. Forecasting, therefore, works best as a map of vulnerability and a measurement of trend, not a dramatic prediction. The boundary is therefore about timing and scale, not about dismissing the danger. Scientists cannot name the next road section or neighborhood that will deform, and the evidence does not support a Siberia-wide collapse. And what they can identify are places where warm ground, buried ice, water, and critical infrastructure overlap. In a chronic hazard, that map of vulnerability is the closest thing to an early warning. A flood ends and leaves a high water mark, while an earthquake leaves a rupture and a clear event time. In permafrost, thaw can leave a maintenance record. The same road leveled again, the same pipe repaired again, the same foundation adjusted after another summer. Its signature is repetition that repetition can become the warning. When a road dip returns, engineers can instrument it instead of only resurfacing it. When a building moves, the change can be compared with ground temperature and water conditions. When residents report new pooling or cracks, those observations can be integrated with satellite maps, making the community part of the monitoring system. And the final image is simple. Imagine a winter road in Yakutia, frozen hard beneath tires and snow. It appears restored because cold has temporarily locked the surface in place below it. A wedge of ancient ice is smaller than it was the year before, and spring returns. Water reaches the weakened layer, and one side of the pavement begins to lower. The crack at the surface is not the beginning, it is the moment the hidden loss becomes visible. For generations, Siberian towns treated frozen ground as permanent geology. The new reality is that permanence has become something engineers must measure, defend, and sometimes redesign. The communities are not sinking all at once. They are losing the certainty that the ground beneath them will stay where it was.